All right, guys, I think there were about 54 questions. Yeah, same as we had on the last test. So 54 questions on the test, and they're pretty much evenly divided between chapters 3, which is energy, work, and metabolism, and then chapter 4, which is sound and hearing and speech production. Uh, They'll be divided up in order, just like we had on the last test. So you'll have the energy problems first, and then you'll have the sound and waves problems next. So it shouldn't be difficult to sort of tell what section you're in as you're going through it. We can go through tests if you like, if you'll have particular questions. It seems like some of you came with particular questions, and those are probably common to all of you. So we'll just start with that. If you have particular questions, I can pull them up.
Can you just give a bigger picture of
Uh-huh. Yes. Um,
there's so much.
all right, y'all. So listen, like in short, though, on the test, everything's on the test. And the notes, the book, the old test, all those are great ways to study. I will tell you that I did pull some questions from old tests, but most of them, practically all of them, were new questions. But they're still covering the same material, so the old tests are good ways to study. But in chapter 3, let's just sort of give you an outline of what we have on all of these. We need to know work and energy. You need to know what work is. That work is equal to a force times a displacement. That you have to have a force and you have to have a displacement. You need to know what is negative and positive work. That negative work means, negative work means that you're taking away energy. So like you're slowing something down like friction does. If I'm doing positive work, that means that I'm giving energy to the thing. I'm speeding it up or giving it potential energy. And so you need to understand that if my force and my displacement are in the same direction, that's positive work. And if they're opposite, that's negative work. You need to understand the work-energy theorem, that if I do work, I change the energy of that material. So all those things we dealt with in sort of the first part of chapter 3. Then you need to understand the different types of energy. And we had kinetic energy. We had potential energy. We had chemical energy. Just sort of understand what those are. We had electrical. We had nuclear. Just you would have a very basic question like, what is chemical energy, for example? And it would be, I don't know, what is chemical energy? It's the energy that's wrapped up in the bonds of the molecules. Nothing too complicated in that. You do need to understand for kinetic energy and potential energy that we did have these formulae for them, 1/2 mv squared and mgh. And so you'll need to know how the kinetic energy depends upon those variables. So for example, if I double the speed, if I double V, that means I quadruple the kinetic energy. You'll also need to know the conservation of energy. No, if you double the mass, so if I have kinetic energy equals 1/2 mv squared, anytime you're dealing with these relationship problems, you just double the thing over here, and then you would double what's over there. Whatever happens to one side, you have to do it to the other side. And where it gets difficult is when I have a squared variable, because then whatever I'm doing to the variable, I have to square it. And when you have a variable that's in the denominator, so then whatever I do to the denominator, I inverse it for the other side. That's where I understand. That's where y'all begin to stumble, right? I understand it. It's not that you're not capable of doing it, and certainly not because you're stupid, right? Because y'all are all really smart. It's new and you haven't done it in a while, and so nothing to be ashamed of. Now, with the conservation of energy, you're going to see the roller coaster bit, right? We did one like this, and you'll need to be able to describe to me what the energies are like along the path of that roller coaster. So, like for example, up here, I have lots of potential energy. I have big potential energy, but very little kinetic energy, if any at all. The kinetic energy is related to the motion. So if it's moving a lot, I have a lot of kinetic energy. And then down here, I have big kinetic energy, but no potential energy, very little potential energy, because the potential energy is related to the height of the object. So you'll see that picture on page 37 or whatever in your notes. You'll see that picture of the roller coaster, and I'll ask you, where is the speed the greatest? Where is the kinetic energy the greatest? Or where is the potential energy the greatest? Jake?
That's on the second, with the second, where it's at.
Did y'all answer your question?
Yes.
Okay.
I mean, it's in the notes.
Okay. Oh yeah, where is equal? Where are U and K equal? Yeah, it's would be like right here, because half of the energy is in potential energy is equal to half of the total energy, and half of the energy is in kinetic energy. And I know that it's half because it's at half the original height. And since it's at half the original height, my potential energy is half its original value. All right. Conservation of energy. You'll need to know power. You need to know all the units. In fact, you might just want to write down all the variables that we have and write down the various units. So work and energy, you know, we have lots of units for that. Let's just write them down. I have joules, calories, big calories. I guess that's all we had. We didn't have any others. For power, oh yeah, Newton meters. Thank you. Newton meters. So those are all work and energy. For power, you might want to make little note cards and quiz yourself on these. Power is watts. What else did we have? You had temperature, degrees Celsius, degrees Fahrenheit, Kelvin. You need to be familiar with those. We had Q. That was joules per second. That's the rate of heat transfer. You had specific heat and the latent heats, but you don't need to know the units for those per se, but you need to know what they mean. So we'll come back to that. And then into chapter 4 for units, what did we have? Frequency, which is 1/seconds, or hertz. We had period, which is seconds. We have wavelength, which is meters. We had some other things in there, but like K, the thermal conductivity, but I won't ask you the units for that, only the sort of the big things. Make sure I'm getting them all. Yeah, I think that. Oh, we had intensity, which is a watt per square meter. Yeah, power over area. Yeah, that's it. So know all those units. Like I said, put them on a card, sort of quiz yourself on them. I think you know them. They're in there. You just need to make sure that you're familiar, that they're at the surface. You need to know what closed systems are. So still stepping through chapter 3. A closed system is no energy in or out. But you can have energy in there. Like you can have things moving around in your system, but there's no energy going in, no energy coming out. Basic idea of what a closed system is. You need to know efficiency. And we can look at some problems, and this is probably a difficult thing for some of y'all. That's where you're dealing with those percentages, but yeah, it does depend what it is. You have to know how to answer all those. Like, what usable work am I getting out, or what am I losing? And those are really the only two questions I can ask. And we'll look at some. So let's lay that aside for now, and we'll come back to it. You need to know what heat is. Remember, heat is not really energy, it's the transfer of thermal energy. So heat is the move of energy from one object to another. And so that's in your notes, it's in the book. You need to know our temperature scales. You need to know what they're based on, the boiling and freezing points of water, the absolute zero and the triple point of water, and that's it. So you need to know what they're based on. And then you also need to know some basic temperatures in the Celsius scale. So in Celsius, 20 degrees Celsius is room temperature. And then about 37, 40 degrees Celsius is body temperature. 37, but if you were to round, it'd be 40. You need to know the phases of matter. Oh, this is where it gets tricky. So you need to know the phases, and you need to know specific heat. The specific heat is the amount of energy required to raise the temperature of that substance by a certain amount. So if it has a high specific heat, that means it needs a lot of energy to raise its temperature. If it has a low specific heat, not much energy to raise its temperature. You need to know latent heat of fusion and vaporization. Okay, this is fusion. Fusion, this has to do with when my material is going from the solid to the liquid or the liquid to the solid phase. Like when something's melting, right? When ice melts, it's losing that amount of energy, the latent heat of fusion. And then the latent heat of vaporization, vapor, right, means when a substance is going from the gas phase to the liquid phase or vice versa, that it requires that amount of energy to go from being a liquid to being a gas. That not only do you have to raise water up to 100 degrees Celsius, like if you just do that, that's not enough, that you have to put in this extra energy in order to make it become a vapor or a gas. And that's the latent heat of vaporization. I'm not going to give you any questions where I say, what is the energy required to change this into a gas? We have to use those equations, Q equals mc delta T or Q equals ml. But you have those equations, but I'm not going to ask you questions where you have to actually calculate those energies. But I will ask you questions that test, do you understand the meaning of specific heat or the meaning of the latent heats? Okay? In fact, there are several questions about that. So make sure that you look back over that particularly, that you understand what those values mean. Read in your book, too. The book is pretty good on that. I would read through the chapters. I know that y'all have read them. It's like I know that you've read them exhaustively preparing for the quizzes and stuff, but I would take another read through. Julian? Sure, either way. So, like if I'm going from a solid to a liquid, that means that I have to put that energy into the substance to break apart those bonds and make it go from a solid to a liquid. It needs energy to break apart those bonds. And likewise, if I'm going from a liquid to a gas, I got to put a lot of energy in there to break it apart. And that's why sweating takes so much energy away, because the latent heat of vaporization for water is so darn high. And when water evaporates off your body, it takes all that energy away from your body. It takes it from your body. Okay, so you need to understand that. There's some heat flow. That's this thing, Q over T is K A delta T over D. And I'm sorry, I gave you the wrong unit here. Q over T is equal to J over S, so make sure you note that. This was the rate of heat transfer. Q is heat. So Q is in joules, and T is in seconds. So it's joules over seconds. I don't think I asked you the units for that, but you do see this on the test. And I ask you, if you change K, if you change A, if you change delta T, or you change D, what happens to the rate of energy transfer? For example, if I doubled this distance, what would that do to Q over T? I would have to do a 1/2 over here. Whatever I do to the right-hand side, I have to do to the left-hand side. And later we'll look through some of the tests and we'll see some questions like that. But for example, another, if I tripled the area, what would that do to the rate of energy transfer? It would triple it, right? Whatever you do to the right-hand side, you also have to do to the left-hand side. There are no quadratic relationships. That means there are no squared numbers in this equation, but there is an inverse relationship with the D.
So the answer to that one would have been 1/2, or would it have been 1?
What, for the...
when you double the distance.
Well, yeah, so it would have been 1/2. So for example, if I told you... Yeah, what if I told you Q over T was equal to 4 joules per second? But then I double D. What is Q over T now? No.
It would be 2.
Yeah, so if D is doubled, now Q over T is equal to 2 joules per second. Because I have this factor of half. I double D, but I have Q over T.
Okay, can we go over some of the math or just like can we like do the exact?
Yes.
Yeah. Okay.
Yes. Okay. Can I finish sort of the overview right quick? You need to know all the food stuff, like all the body stuff. You need to know the lipids, all the nutrients, lipids, carbs, proteins. Also, don't forget nutrients include water, right? Water is a nutrient. And vitamins and minerals, those are nutrients. Sort of know what we talked about with energy from food. You're going to see some efficiency problems related to the body, that the body's not very efficient, right, at taking the energy that you give it and then producing usable work. So we'll see that. You need to know BMR, TMR, have some idea of what these are. This is roughly 1,500 calories per day. Big C. And TMR is about, well, it depends how much activity you have, 2,000 to 2,500 calories per day. You need to know the heat loss of the body, conduction, convection, and radiation. Which one's the biggest? Radiation, right. But we also put in evaporation there. It's not really a method of heat loss, but a lot of heat loss occurs through evaporation, which is sweating. But still, the biggest way of heat loss is radiation. You need to know the ways that we stay cool or warm. Everything, really. Cool or warm. Shivering, the dilation or contraction of the blood vessels that send blood to the skin. And if you want to cool off, you send blood to the skin. If you want to stay warm, you keep that blood deep down inside your body. Hyperthermia, hypothermia. Yeah, not really any of that. Okay, and then y'all want to look at these now, and then I can come back to chapter 4. You want to do a quick overview of chapter 4? Okay, all right. Let's do some problems, and then if we need an overview of chapter 4, we can do so. What you got there?
Oh, I had some from every test.
Well, go ahead and just call them out to me.
Okay. This is exam 2, spring 14.
Okay.
Okay, and it's number 30. Yeah, I have that.
All right, you drop a ball from a height of 5 meters. What velocity when it reaches the ground? You're not going to have, I don't think there are any calculations like that. There are 1 or 2 calculations that are simple, but not like that. So we didn't really do anything like that in class, so no.
Don't worry about it.
Okay. What else you got?
31. Yeah.
That
one I thought, would it be like, I had 20.
Let me work the question, but I'm going to give it a caveat that while you'll see efficiency, it won't be this involved. It's going to be a lot simpler than this, okay? And again, you're going back pretty far in my test, so I've changed sort of the way I teach the course. But it's still, efficiency is still important. So let me just...
I'm sure I had another one.
So the input work here is 80 joules. That's the work that the engine requires. The output work is equal to our change in potential energy, which is going to be equal to mgh, which is 2 times 10 times 1. 2 kilograms times 10 meters per second squared, that's g, right? Times the height, and so that's 20 joules. I'm putting in 80 joules, but I only get out 20 joules. What's that efficiency? If I put in 80, but I only get out 20, I only got out like a quarter of what I put in, right? So the efficiency is equal to work out over work in. That's 20 over 80, which is a quarter, or 25%. Yeah, I'm going to give you the workout and work in, okay? But I'll want to know then, or I might give you the work in and then give you the efficiency, and ask you either what is the usable work that you get out, or how much energy are you losing. Like if you put in 100 joules and you have 30% efficiency, how many joules do I get out that's usable? No, the usable work I'd get out would be 30. And the non-usable, the energy loss would be 70 joules. I'd lose 70 joules. You know, the work in is the energy that you're putting in. So that's like the food that you eat, right? And then the work out is the actual mechanical work that you're doing, the usable energy.
A non-math question.
Okay, let's hear it.
The same test, 53. It says the correct answer is D, but it's saying produces heat, and I know like sweating is losing heat, and the dilation of the blood vessels is losing.
Okay, I might have changed it. Let me think. So, which is the way that produces? So you can produce heat by shivering.
Yes.
And increasing the BMR.
Yeah. So
right.
To us, it would be C.
2 and 4.
That's what I meant, but that's not an answer.
Yeah, the answer is 2 and 4. I don't know what the deal is. I probably changed it. It was just a mistake.
Okay.
Not sure if y'all know this about me, but I'm not perfect. Did you? Nobody's perfect. And y'all are pretty close, but you're not perfect either. Okay?
All right.
Okay. What you got?
This test is spring 2016, exam 3.
This is useful for y'all?
Yeah, exam 3.
Is this useful for y'all? Yes, useful. Okay, which one?
Number 10.
Okay.
I don't even know what formula you use.
Oh, yes, you do. Yes, you do. So this is a two-step problem, and you will have to, I'll give you the wavelength, the period, and or the frequency, and you'll have to be able to calculate those various things. There are really two formulae that are involved here.
It's exam 3, spring 2016.
So here, can y'all see this okay? Y'all can see that? Adam, you can see it okay? I can zoom in a little bit. I can barely see it. I'm right here. What's the number I'm looking at? 10. Okay, so a sound wave travels at a speed of 1,000 meters per second. In a solid medium, the wavelength is 0.5 meters, and I want to know what is the frequency. Now, I know that frequency is 1 over period. That's on your equation sheet. So I need to find out the period. And I know that V is equal to lambda divided by T. So I know that 1,000 is equal to, oh no, an easier way is I also know that V is equal to lambda times F. That's also on your equation sheet, I think. Because frequency is 1 over period. Now, so V is 1,000 meters per second. Lambda is 0.5 meters. And I want to know what is the frequency. Well, half of what is 1,000? No? Half of what will give me 1,000? 2,000. Now, I show you that with a caveat that, like, I understand that just dealing with numbers is kind of hard for y'all.
Yeah.
I understand that. And so I've tried to make the numbers as easy as possible. Like, I've tried to make them, like this would never make it on my test now, just because the numbers are, fractions, and I don't want y'all to mess up on the numbers. I want you to get the physics.
So you got that because you know that you need to multiply the frequency by 1/2 to get 1/2.
Right. Now, if I were to actually follow the algebra, what I would do, I'd divide by 0.5, divide by 0.5, and 1,000 divided by 0.5 is equal to 2,000. Mm-hmm. But, as I said, I try to make, these numbers wouldn't cut it with me, that I would make them much easier numbers. So, don't be afraid. Don't be afraid, but be prepared to. You don't need a calculator. I don't think that a calculator is going to help. That the actual calculations are like 4 divided by 2. Okay? There are 3 times 4. Okay? I try to make the numbers as simple as possible. And then really there may be 2 or 3 calculation problems on the entire test. I tried to limit that as much as possible. Yeah. So even if you just skip those, you'll still get an 8. The calculation problems. There aren't that many. Now there are some relationship problems too. And that's math too, I understand.
Yeah.
But even those, they're limited. Okay? Okay. 22?
Oh, that's from a different test.
Yeah.
Oh.
I marked it, but it was going on and I forgot we're not doing that.
Oh, yes. Yeah, we're not doing that yet. We'll do that on the next exam. All right, what's next then?
Next test is exam 3, fall 2018.
Y'all good with that? Okay, we can come back. Exam 3, fall 2018. Which one?
22. I think I did it now, but I want you to go over the test.
Okay, you stand 1 meter from a point source of sound. And the intensity is I. You move 0.5 meters closer. What is the new intensity? First of all, is it going to be bigger or smaller? If you move closer, it's going to be bigger. So we could get rid of the C, D, and E. It's either 4I or 2I. And I know that I is equal to power divided by area. However, and this is where it gets, this is where we separate the sheep and the goats. That area is 4 pi r squared. I think that's also on your equation sheet, but I think it's a separate equation. Is that right? The area of a sphere? I think it is. And so now, if I have r, if I have this value, it's squared, so I get I over 1/4. But that would be 4I. Like, that would be okay for the test, okay? I want y'all to know how to do that, how to deal with inverse and quadratic relationships.
Okay, I'll put it in.
How'd you think of it?
I did like, okay, so you moved 1/2 meters closer, so I did 1/2, and then just inverse 1/2 and square the 2. Would that work?
Well, that's the same as what I did,
Okay.
okay? But I don't know if you were thinking the right way. Like, what you did with the numbers was right, but I'm not sure if you were thinking about it the right way.
After you explained it in class, I think I understood.
Okay.
Because I was like thinking of it in addition, but you said it's more like multiplication.
It is multiplication, right? It's factor. Okay?
Okay.
Yeah, in class we were talking about you're moving from 4 meters to 2 meters.
Yes, but it's still only 2.
Right. It's a factor of a half because your distance decreased by 2, by a factor of a 2. Not subtraction,
Yeah.
although that's true. It did decrease by subtraction by 2. But the important part is the factor by which it changed.
Yes, because at first I was thinking it was 4, so I was like, why is it not 1/16? But it's because it's a factor.
Right. Like if I went from 9 to 3, that would be a factor of a third, not 6. Okay, what you got? Okay, 100 decibels is how many times as intense as 80 decibels? Decibels are easy. All you gotta do is say 100 minus 80 equals 20, right? That's equal to 20. I subtract the 2, and then I just get rid of the 0, and I say 10 to that, 10 to the second power. Okay? That's all you gotta do. And the decibels that I give you, they're gonna be factors of 10, so they'll be like that. So if it's 170, it would be 10 to the third power. If it was 160, it's going to be 10 to the fourth power. And remember, 10 squared is 100, 10 cubed is 1,000. Huh?
You just add that many zeros.
You just add that many zeros. So here, the answer is 100, right? Because this is 20, the difference. You take the 0 off of 20, 10 squared is 100. And you will have a question like that. And it's going to be 10, or it's going to be, yeah, you could do that. It's going to be 100, 1,000, 10,000, 100,000. Really, I just want you to understand that decibels are a logarithmic scale. That a little change in the decibels means a big change in the intensity.
30 and 31. Yeah, is that
I understand
Bernoulli effect?
how you got them, but I just want to.
Yeah, that's the Bernoulli effect. We did talk about 30 and 31. That when V goes up, the pressure goes down. And so with, these are your vocal cords. With their vocal cords, when you send a whoosh of air through them, you see that's the wind blowing through the vocal cords, they create a low pressure because when V goes up, P goes down. And when you get that low pressure, those vocal cords, they come back together again. And the same is true for sheets of paper. I don't think we did this in class. Sorry. I don't know if it'll work with these. We'll try. But same as with sheets of paper. And if I blow through them, they'll come together. Like, you see? Like, doesn't it seem like they would just blow apart? But they don't. In fact, the more you blow, it's like the harder they try to come together. Now, they do blow apart a little bit just to let the air through, but they don't go flying apart. Same is true on the interstate. Tell your friends this, that when you go on the interstate and you go up next to a big truck, you get the Bernoulli effect. Sometimes you're driving next to a big truck, it feels like it's trying to suck you up. And it does try to suck you up a little bit because you got the high velocity air going between those two flat surfaces. Okay?
Oh, yeah. Yeah,
40. I'm just understand the word.
Oh, yeah.
Okay.
Yeah. That's what I have something about too.
Oh.
All right, let's look at 40 since I'm here. So I want to find the frequency. And in order to find the frequency, I need to find the period. Let's see if I can write on this. I'm going to try. So to find the period, I can't. It's the time between here and here. Or I could say here and here. So the period on this is 2 seconds. I look for the time for one complete oscillation. So starting here, I would go all the way over to here, from 2 seconds to 4 seconds. I skip over the middle because that's just a half an oscillation. It goes up, goes down, and it comes back. So that is one full oscillation. And that's the time for one full oscillation is 2 seconds. That's our period. And so the frequency is 1/2 hertz, half a hertz, 0.5.
Are the wavelength and the period the same thing?
The wavelength and the period are similar, but you can't get the wavelength off of this graph because it's a history graph.
Okay.
And you can't get the wavelength off a history graph.
So wavelength is the distance.
But you're right, yeah. Just a second, we'll come to you. So the wavelength and the period you find in the same way, except you find the period from a history graph and the wavelength from a snapshot graph. All right, Julian?
Could you, like, for this one, I mean, I understand this, but could you just look at, like, the distance between, like, a peak? Like, you see how the
Yeah.
from 0 to 1 is, okay.
Yeah, you could do peak to peak. That's still an oscillation. So coming up, go down, come back up again. That's one full oscillation. The reason I did it from here to here is because they were on even numbers. But peak to peak would be like 0.5 to 2.5, which would be 2 seconds.
I meant what, from 0 to 1, how it's going up right in the middle of those constants? That's like a half, right? That's all I was looking at. This might just be this particular graph.
No, you can't do that. Now you have to find the period. And to find the period, you have to go through one complete oscillation. What you can do here, go down, down, and then I'm at 2 seconds. That's one full oscillation. Don't trust the graph.
No,
Just
like how it's drawn.
oh, okay.
They always tell you on the ACT, like, if a triangle looks like it's equal, don't, like...
Sure. Yeah. Mm-hmm. Yeah. All right. Was there another one on this one?
I think that's
43 or 44.
You said wave was found.
Yeah. So if I want to find the wavelength, Yeah, this is a snapshot graph.
Which is X and Y.
Yeah, X and Y, or Y and X. The other one was a history graph. And you know history because it has time on the axis. And you know, history, time. History is the passage of time. Goodness bless you. So this is the same way to find a wavelength as we did for the period. You start here and you go through one full oscillation from 0 to 3. So the wavelength is 3 meters. One full oscillation. You can go in other places too. Like let's say you could go here, 4, and then go back up and it stops at 7. So 4 to 7. And then that would be 3 meters. What was the other one? Okay, 43. You're going to see this for sure. 43, the wavelength is 2 meters. The speed is 4 meters per second. And I want to know what is the frequency. And then I have 2 ways I can do this. The easiest way is to say that V is equal to wavelength times frequency. So that's 4 is equal to 2 meters times the frequency. And so my frequency, I divide both sides by 2. The frequency is equal to 2 hertz. When I say the numbers are easy, they're sort of that level. I don't really care if you can divide 2 numbers. I do care, but I want you to understand like how these variables are related to one another. But you could do that, right? All right, that's okay. And I try to do the numbers, like all the values that you're working with. So I know you do in your head and all that. I try to do them so that they're nice, big, nice numbers that divide or multiply easily. Don't be afraid, right? Be a little bit afraid so you're prepared, but don't come in all anxious. You're gonna have plenty of time. It's an hour and 20 minutes, huh? No, you don't want to live that way. Like that's just you're not gonna sleep well. Your body's not gonna be well. In a bad way to live.
I dream about something.
Good, yeah, so do I.
I'm making like tests and I'm
Okay, what else?
So the 44.
Oh yeah, so what is the wave's period? Well, I know that frequency is 1 over period. So if I wanted to find the period, period is 1 over frequency. Y'all see what I did there? Yeah? And so if frequency is 2 hertz, the period is a half a second. Another way that you can think of it is, I'll do it in red here. V is equal to lambda over T. And so I give you V, it's 4 meters per second. I give you lambda, it was what, 2 meters. And you need to find T, capital T, period. And so to do that, you can cross multiply. So 4T equals 2. So T equals 2 divided by 4, or half a second. I don't know. Let's look and see. I don't remember. I do? And look at me. Well, no, it's in. She's asking, is it on the equation sheet? I think. Is that what you're looking at?
Yeah. V equals wavelength over period.
Yeah, V equals frequency times wavelength right there. Y'all can see that with your awesome eyes. And then this lambda over T is V. Yeah, so you have all 3 of those, and then the frequency is 1 over period. Oh, and look, I even gave you this. Intensity is P over 4 pi r squared. Okay? You're not going to see these expressions, but I certainly will ask you questions about how is the frequency related to the tension, the mass, or the length of the string. We talked about that quite a bit, right? And that's true. That's important for your vocal cords, too. The length, the mass, and the tension changes the pitch. You'll need to know pitch and volume, what those are related to, right? Pitch is what? Frequency. Volume is amplitude, right?
What is frequency describing? Like pitch?
The pitch. Yeah, so frequency.
That wasn't an option.
What number is it, or what test is it?
Exam 3 in spring of 7.
Oh, yeah.
There's a review on the graph.
So frequency describes.
What is it? Exam 3 spring of 7.
Yeah, so frequency describes the number of crests in a wave that pass a point in a given time. So we had a problem early on in this chapter where I showed you two waves. These are history graphs. There's one, that one. All right, and which one has the bigger frequency? The second one has the bigger frequency because in a given time, there are more crests. So you see, if I pick a time, there's only 2 crests in this one, but there's 1, 2, 3, 4 crests in this one. So the bottom one has twice the frequency.
What is
That was number 24. But it's important for you to understand that about frequency too.
Well, we have like the ones where you give us different ones, and I was getting that one right, but I was like, so why don't I know what I do?
You do know it, yes. Okay? Huh? The same one?
Yeah.
Yeah, that's the point. That you don't need the amplitude, right? That I know that V is equal to lambda over T. V is 100 meters per second. Lambda is 2. And I want to know what T is. Is that right? Lambda? Oh, I want to know the frequency, yeah. So V is equal to lambda times frequency. And so V is 100. Lambda is 2. And so what is the frequency? What times 2 equals 100? 50. All right. Yeah, don't be thrown off. I like to do that sometimes. Just throw in extra information. But you're right. You don't need the amplitude. The amplitude doesn't change the frequency. Like if I just talk louder, it doesn't change the pitch of my voice. It only changes the volume. It makes sense when you know it, but if you're not familiar with it, then it'll be difficult. All right, what else, y'all? All right, again, be careful going back that far.
There's just one that confuses me because.
Which one?
Okay, so it's 44 and 45. It talks about like the vocal cords determining like. Wait, it's 45 and 46. So 45 is the answer is the tension.
Mm-hmm.
But 46 is the vocal cords are longer. And like they both determine.
Okay.
Pitch.
Right. So remember that the frequency is 1 over, what is it, 2L square root of T over mu, where L is the length, T is the tension, and mu is the mass density. So the frequency that's produced by a vibrating string is dependent upon the length, the mass, and the tension, A, B, or C. But in an individual, in a person, you can't change the mass. Yeah. I don't know. Is Chrissy here? Yeah. Do y'all see a wallet anywhere? Rosie is here. See it in here? Yeah. All right. Where is that? Oh, so for an individual, you can't change the length or the mass of your vocal cords. For like me, I can't change that. It's just not possible. But I can change the tension, and that's how we talk. I or woo, right? I change the tension in those vocal cords. So 45 is the tension. But then on 46, men, this is different. how are their vocal cords different from, say, women's vocal cords? They're longer, right? And they might even be more massive, but mainly they're longer.
Yeah, because there is another question, and I think the answer was that they're more massive.
But not for this, not for men's vocal cords. It might have been like on a guitar, like a bass guitar. Those strings are more massive than an acoustic guitar or a six-string guitar. Okay, is that clear?
So the bottom.
The speed of a wave is dependent on what? This is very important. The medium only. Even though, remember, we said that V is equal to F times lambda? But if I change F, that doesn't change the speed. Or if I change lambda, that doesn't change the speed. If I change F, lambda changes, but not the speed. That it's only dependent upon the medium. And then don't forget, too, that waves travel faster in a solid. And that's not intuitive. Like, you probably didn't know that before this class. But waves travel a lot faster in solids, like steel. Yeah, you don't need to know that number. But they travel a lot faster in solids, and then next in liquids, and then finally slowest in gases. Okay. It's crazy. Shouldn't be that way. Talk to somebody about that business. Do you have a question?
No, did you want to which sound travel faster between helium and air, and it was helium.
Right.
Okay, but then
Why is that? That's a different thing.
all the molecules.
Right. Think about it. The molecules just have less inertia. The helium molecules, just because they're less massive, they're a lot smaller, and they can move around a lot faster, and that means that the sound can transfer its energy more quickly. Oh, it would still travel faster in the solid. Yeah, it's a lot faster in the solid.
If you give us like elements in the periodic table and we don't know which one's the smallest, but we know that the smallest one.
It's right there.
Yeah, I know, but
And right there.
so smallest. All of these are smallest on each side, right?
Well, but the numbers, the red number,
At the bottom it's an ass.
Oh,
and they're all in order, so like.
yeah, I mean, y'all know that hydrogen and helium are the smallest molecules of all, right? Or smallest atoms. Y'all know that? They're 1 and 2. You can't get any smaller than that. So if you have a question like that, it will be obvious that it'll be like that one that I gave you. Helium versus, what was it, like oxygen and nitrogen. Those are big compared to helium. They're like 7, 8 times as big. Is that, I mean, I don't say it's obvious, but do you know that? Air is heavier than helium. That's why helium floats. Okay.
You know, that just clicked.
Okay, what else?
This one's just one of those thermal conduction questions.
All right, which question?
Number 40. I just want to work it again. So I don't want to say that.
Yeah, and there is a question like this. I forget it's the exact same question. I just changed the numbers and changed sort of what I was asking. All right, but here,
Exact same question, but I changed everything about it.
I just changed the numbers really. So Q over T originally is 2 kilocalories per second. But then I double A. So Q over T is K A delta T over D. So then I come in and I double the area. That means I'm going to double Q over T.
Okay.
So whereas it was 2 kilocalories per second, now it's going to be 4 kilocalories per second. But note, what if I had doubled, D? Then I would have Q over T. And if I'd done that, then this would have become 1 kilocalorie per second. That's really all that I could do.
So what was the other one? Why was the other one different? Why was the other one 1/2 instead of 1? That we did.
I'm just gonna get this wrong, honestly.
No, you're not going to get it wrong.
Okay, so this one's 4 because just 2 times 4 because area is squared.
No, area is not squared. Oh, I know what you're saying. Yeah, so here I'm just doubling the area. And the area, I'm just doubling this quantity. This quantity is not squared. Area is not squared. If I was saying I was doubling...
Meters squared.
I know, but this variable is not squared. The previous one, we were looking at intensity. And in that one, the intensity is energy over 4 pi r squared. Like there, this variable is in fact squared. And so that was the difference. So if I double this quantity, I quarter this quantity. Because it's 2 squared. But in this thermal conduction equation, none of these quantities are squared.
That's why I don't get why it's 4. Because we got, because I
Like, it's hard to
Mhm.
it's, you have to know it's 2 kilocalories.
Yeah, it was originally 2.
So it's not zero, it's not starting off as 1, it's starting off as 2, so if
Okay.
you're doubling
Right.
2, it's 4,
Mhm.
right?
Okay.
That's right. That's right.
But if it started off as 1 kcal, then it would be 2.
That's right. Because I would multiply it times 2.
If it started off with 3, you double it to 6.
That's right. You're right. If it started off as 54, it would be 108.
That's too,
That's too big. I know. No, I'm getting okay with this. Like, I'm okay with y'all being a little bit afraid of numbers. Like, it's starting to grow on me just a little bit.
I'm glad. It'll be all semester long.
Okay, what else?
So that's why, because you're multiplying 2 times 1/2, that's why.
Mm-hmm. You got it? Y'all got it? Yeah. It's easy to have it here. It's hard to have it tomorrow when you're all by yourself. Okay? So you need practice, practice, practice. Like, it's easy. I show it to you. It's like, oh, yeah, of course.
Right.
But
And then if we do it on our own, it's like.
on your own, and practice, practice, practice. That's what helps. So I don't mean to scare you, but I'm just saying that that's the reality of it. Okay?
Can you show us another, like, if we were doing intensity, like, what would be the question for that?
Oh, goodness. Let's see. Is there one in this test? Let's see. This is what? Exam 2? Let's look. Let's just see if there's one on exam 3. I usually have at least one. No, I guess I didn't have one on here. So let's say that you're standing next to an object and the intensity is 4 watts per square meter. And you're standing at a distance equal to 8 meters. Okay? That's going to be okay. And then I move to a distance equal to 4 meters. And now I want to know what is my new intensity. First of all, is the intensity going to be bigger or smaller?
So it's going to be bigger.
You're getting closer to the speaker, so it's going to sound louder. So that's the first question that you ask. It's going to be, so I know, has to be bigger than 4. And D has increased with a factor, or a factor of a half, yeah. So it's times a half. Now I write my equation. I is equal to P over 4 pi r squared. But R, or D or whatever, I'm having that, but it's squared. So this is over 1/4. When I have a 1/4 in the denominator, this whole thing becomes 4i, which jives with what I think it should be, that it should be bigger. It shouldn't be 1/4 of 4. It should be 4 times 4. And so the answer would be 16. I've halved the distance.
Shouldn't it be 4?
No, it shouldn't be 4, because it was originally 4.
Oh.
And then I multiply it times 4 to become 16. Then my intensity increases by a factor of 4, going from 4 to 4 times 4, which is 16. Yeah, my distance, I go from 8 to 4, so I'm multiplying 8 times a half to get 4. So my distance, that's where this half comes from in this one.
And then you're squaring it, you have, that's 4, so you have that on the other side.
Right, because r is squared, it's half squared, and because it's in the denominator, it goes in the denominator over here. But when I have a fraction in the denominator, I have to flip it and bring it back up. So this 4 comes up, and I multiply I times 4. Like, that's probably the most difficult question on your test. No, don't miss it. Like, try to get that one right.
Try.
I want 100%. You should get 100%.
I want 100% too.
Over here. How about one of these nice questions where you have like, who's the best person?
Yeah.
I
love those.
Or like question 8, bubble 8 or whatever, test 8.
Yeah. Even like the definitions. The definitions are easy.
He's already in my test, so let's just.
There's a lot of there's just a lot of. Do you know what this is?
Yep,
I know that.
I know, and you're gonna get them. All right, but be careful. Just make sure that you're reading them carefully. All right. I'm gonna have to call it a quits if that's okay.
Yeah, that works.
All right.
The top stuff